Hey there everyone, welcome to the next video lecture of this series or this chapter. So far, our last lecture would have spoke briefly about the amount of ATP we could expect for each metabolic substrate that we start with or that we utilize, and looking at the biochemical pathways that are used to metabolize those substrates. This will hopefully give you a better picture and a more applicable way to look at metabolic substrates and when and how they are used. So, for example, at what sort of activity level or what sort of activities might we expect different metabolic substrates and, of course, their pathways be utilized to help produce ATP. So I feel that this is a more comprehensive lecture that pulls together some more practical ways of viewing how we produce ATP for our bodies and from what metabolic substrates, versus a bit more of the technical or detail orientated with the quantitative numbers of ATP from last lecture. Okay, so let's dive into this. And first we're going to look at what sort of interactions can result or occur with our activity levels and the metabolic substrates. And largely, which substrate we use depends on the availability of that substrate, how much energy produced by that substrate, the intensity of our activity, and the duration of that activity. So again, it's kind of like how much of the substrate's around, how much energy will it make for us, and what is the demand of the amount of energy that our body is needing based off of the activity level we're doing, so the intensity and the duration. Now, after a meal, generally we start catabolizing or metabolizing whatever food we have most of. And that kind of gets priority, I guess you could say. So the example here, they try to highlight that if you have a high carbohydrate diet, your carbohydrates start getting metabolized first and used for energy. And if you have a high fat diet, those are the types of energy that will start to be metabolized. And to consider this too is it happens after you've eaten the meal. So one example is when you go to do physical activity, having a meal, let's say a couple hours before you do this activity, of the substrate that you'll primarily want to be using during that activity is generally encouraged. And this is one of the reasons for that, okay? It mentions a little, the slide mentions here a little bit that some protein gets utilized for exercise, where anything less than 60 minutes you'll notice is pretty negligible. But once you start getting up to 5 hours plus, then it starts increasing in the amount of protein metabolizing that you'll see. And from previous lectures, you'll notice that my examples for the rare times during physical activity that protein gets metabolized is very long distance or endurance based kind of activities. Ironman triathlons, Ultraman, ultra marathons, those sorts of activities that, as you can see, are here 5 to 10, sometimes even longer, 12 to 17 hours in duration. That's when protein starts getting utilized. So pretty extreme cases, or during a starvation sort of scenario where the body is extremely hungry and deprived of food. So, what we'll look at here for the anaerobic and aerobic conditions is, you'll see, again, this has to do with intensity and duration. With anaerobic activity, so we're talking about our ATP and PC, ATP, PC energy systems. It's primarily glucose, which we've spoken about before. So no protein, no lipids involved in creating energy at those for that energy systems. But when we talk about aerobics, so your Krebs and ETC, as we've mentioned previously, you'll primarily use carbs and triglycerides, and primarily free fatty acids for that. So let's, again, as far as availability and the amount of energy that each can contribute, we spoke to that a little bit already, but let's dive into how intensity and duration affect the use of either carbohydrates or triglycerides, in particular with the aerobic energy systems. So we can see here when we're at rest, so probably what your state right now is, we get about 1/3 of our energy from carbohydrates and 2/3 from fats. So with that 2/3 coming from fats, that's again just at our resting state. No energy demand kind of made above that level. But as soon as we start increasing in our intensity, so we start exercising, we start moving, maybe doing things around your home, we'll notice that this percentage proportion, so 1/3 carbs, 2/3 fat from rest, starts shifting towards carbohydrate use. Now, if we look at kind of like an extreme point, so maximal exercise intensity, so we kind of had rest, a little bit of a shift from more and more exercise intensity to maximal intensity. We'll see in theory, you should be using about 100% carbohydrates in working muscles. And so much so that some max levels potentially could be even up to 115% potentially. So how and why does this happen? Well, some factors that contribute to this is some factors that are involved in that is carbohydrates produce more energy per liter of volume of oxygen. Now, this is taking into consideration both glycolysis as well as aerobic respiration. And so when you look at all the way through our complete energy systems, we can see we get more per liter of oxygen when we respire for exercise than any other substrate. To kind of illustrate this, 66% is from fat when we're at rest, as far as where we get our ATP from, and that's because it's efficient at the volume it produces. When we look at triglycerides or free fatty acids being utilized to produce energy versus a glucose molecule that goes through glycolysis into Krebs, into ETC, there's a greater amount of energy that way. So per oxygen that gets accepted at the end of aerobic respiration, we see carbs are the greater metabolic ATP producers in this capacity. Another reason why we can, when we're talking about maximal energy intensity and carb use, is our fast twitch muscle fibers. We haven't spoken about this much, but we will dive into it before your midterm as far as topics. And with fast twitch muscle fibers, they produce force. So when we're producing force, that's high intensity. We highly use glycolysis, and of course that uses carbohydrates or glucose as its main precursor for that biochemical process. Next point is our hormonal changes that occur. We'll speak to this a bit later as well. There's a hormone called epinephrine, which stimulates our glycolytic or glycolysis enzymes, so that'll help increase that use. Again, glucose or carbohydrates is our main precursor for this. And last but not least, we have increased lactate from glycolysis. And so when we have that lactate as an end product of glycolysis, what will happen is it'll decrease the availability of free fatty acids or triglycerides that are getting used, which means less fat use, more carb use, because we need to be getting our energy from somewhere. And again, you can think of carbohydrates as like rocket fuel, okay? They're quick burning, high intensity sort of fuel for our bodies, okay? So that's in regards to intensity as we go from rest to maximal intensity. But what if we look at duration of exercise? So we'll see that if we're starting, again, kind of from rest and slowly building up in intensity, our low intensity, long duration, so we're talking about duration here. We can't do high intensity, high duration, or long duration. Our bodies can't handle that. So typically when you're talking about long duration activity, you're talking about low intensity. So what happens in these sort of scenarios is we start again with that high percentage of fat utilization, and it stays there. But as we continue on for longer activities, as long as the intensity is low, you're going to see an increase in lipase activity. So those are the enzymes that help break down lipids, right? And break down our triglycerides to be free fatty acids so that we can use that for Krebs and ETC, okay? So that's generally what happens as far as the hormonal response. If we look at insulin, which is a type of hormone, but it acts more for carbohydrates. So as we increase in insulin, and we'll cover this in a later unit in more detail, but you might have heard of insulin already just based off of, if you know someone who's a diabetic, you might know a little bit about this, but insulin brings energy or carbohydrates into the cell, into the muscles to work. So what happens is if you have a high carbohydrate meal, insulin will go up because all this carbohydrates or glucose is going to be spiking your blood sugar. So we have all this glucose in the blood, but with an insulin, we want all that glucose in the blood to get into the muscles. Okay, so if that's the scenario, and if you remember back to a previous slide, when you eat a meal high in carbs or high in fat, you tend to use more carbs or more fat depending on what you ingested. So this explains that when you have a high carb meal, you'll tend to have more carbohydrates available. You'll tend to use that more. So this process, when insulin gets released into into our bodies and our bloodstream, is it decreases triglyceride use, because your body's like, whoa, we got tons of glucose here to be used. Let's use that before we start breaking down our storage of triglycerides and making free fatty acids. We don't need that. We have lots of glucose right now. So there's this positive feedback or negative feedback loop, of insulin decreasing triglyceride use. Okay, so that's if you eat a lot of insulin. But and then, so yeah, again, just to reiterate, during long duration, low intensity activities, they use an example of a marathon. What can happen over time is we start depleting our glycogen storage, those stored glucose chains in our body. And what can happen is you can hit the wall. Okay, if you've ever seen some videos, and you can Google this if you haven't seen it yet, you can say Ironman triathlon finisher collapses, okay, videos, and you'll see these people that literally can't stand. They don't look like they know what's going on. And really what's happened at that point in time is they're so depleted of energy that they're just like losing function of their body. Now that's a bit of an extreme example, but it's definitely a good illustration of what hitting the wall can look like, for sure. I, during a marathon one time, did hit the wall as well, and it was about 33 kilometers into a 42 kilometer run. And what had happened is I just didn't keep up with my nutrition as far as intaking energy. Essentially I just started running, and you just kind of start walking. Like you kind of go a little hazy, and you feel like your body just stops. You didn't want it to, it just does. And luckily for me, it was very mild, and I was able to get some they have gels, which is just essentially like sugar in a little package with different flavorings. So I got one of those in me fairly quick, and away I went. Within a couple of minutes, I was back at it. So it can be pretty. I don't want to say intense, but it happens for sure. And so the note here says before 60 minutes, carbohydrate drinks or gels are likely not to improve performance. So what that means is from about an hour, depending on the intensity activity, to 2 hours, your muscles and your liver have enough glycogen storage that it can sustain that kind of fuel needed for activity as far as carbohydrates is concerned. But if you don't keep on top of that nutrition before the 60 or 120 minutes, and all of a sudden you run out of this fuel, again, remember, carbohydrates are kind of like jet fuel to make this flame that allows Krebs and etc. to occur, some of these precursors at a reasonable rate, you'll hit the wall, right? That's kind of the idea behind that. So again, the Coles notes is you want to get energy in your long activities within the first hour, even though technically you have enough storage for it, if your activity level is going to be 2, 3, 4 hours long, okay? But under an hour, again, depending on the intensity, the duration is long but the intensity is low, you typically don't need to take in any extra carbohydrates. You usually have enough storage in your body. Okay, so we spoke about intensity, duration. Let's see how that's represented. So I really like this. I'll explain the axes and then explain what's going on in the graph. So on this side we have percentage of energy from carbohydrates and triglycerides, so 0 to 100%. Can't have more 100%, and these two will add up to be 100% based off of their use. And then down here is percentage of VO2 max. We haven't spoken about VO2 max yet, but it's this concept where it's the amount of oxygen you can exchange maximally for yourself. So at the top end of your effort level, the amount of volume exchange that you have with oxygen, that's kind of a marker for your workload or your output capacity for any activity. Okay, so here we'll see if we're at rest, roughly we have about 1/3 coming from carbohydrates and 2/3 coming from triglycerides or free fatty acids, as we spoke about before. Then we'll see that we have this little crossover point, roughly about 35% of our VO2 max, where all of a sudden we get to this point where now we start hitting aerobic activity, and our intensity is such that we start seeing an increase in carbohydrate use. Okay, so the more intense or the bigger workload of our VO2 max that we demand by doing the activity we're doing, we're going to see an increase in carbohydrates. And of course, the more and more we use carbohydrates, the less use and the more negative feedback loop we have for triglyceride use, so we have less and less of that. Okay, so again, maximum effort means maximum carbs. At rest, we have a bit of a share between the two. And again, that's because when we're at rest, even though our aerobic system, so Krebs and ETC, are primarily our sources for fuel and ATP, we always have this low level of glycolytic or of use being producing our energy for us. Okay. Now, I find this leads nicely into a conversation about something, a concept that's going to be really important for the next lecture, something called lactate threshold. And so this has to do with intensity levels, right? We're kind of on the topic of intensity, and we're going to talk speaking about how when we're maximally exercising, we need lots of carbohydrates and this concept of VO2 max. Well, there's this threshold level where, again, is very similar to a crossover point, but there's this threshold where we go from a very sustainable activity level to one where we can't sustain anymore, and that's called our lactate threshold. So OBLA, or onset of blood lactate accumulation, is this point in exercise where we start we have this accumulation of blood lactate at about 4 or greater millimoles of lactate per liter of blood. Okay, we'll see a graph of this in a second. So our lactate threshold essentially is anything above this we can't sustain. Anything below it we could sustain for a very long duration of time. Okay, and we'll see that this work output of our VO2 max, or the maximum amount of oxygen we can consume for exercise, in untrained individuals is about 50 to 60%. So of their 100%, once you get to about halfway, that point after is a tipping point where we just start accumulating lots of lactate. Okay, right. In endurance-trained individuals, that moves up somewhere between 65 to, for like lesser trained endurance athletes or hobbyists, let's say, up to 80% of their maximum workload is under this threshold. So that means if two individuals, one untrained and one was endurance, had the same VO2 max, which typically they don't, so the same proportion of work, the endurance trained person won't hit that lactate or that threshold until about 80%, let's say, whereas the untrained will a lot sooner, which means as soon as they hit that threshold, they can't do any more work past that percentage, whereas the trained individual can for about another 30% before their body starts backlogging in lactate and byproducts, right? So just to remind you why that might be important for this is if we scoot back here and see and remember that increased lactate from glycolysis, which again, if we hit that threshold where things start backlogging, will inhibit triglyceride use. So what are we really saying when an individual hits threshold? Well, we're saying that they can't use or use less and less, or essentially very little, free fatty acid for fueling their activity. Which again, if you tie that back into the point where, if you recall, we have a finite amount of the stored glycogen. We have a finite amount of carbohydrates in our bodies relative to fatty acids. So again, that's what that hitting the wall is partly related to, is working above this threshold too long, okay? So you work above this threshold too long, and then you're done. And so how does training come into play? Well, I think we're gonna, before we finish the last 2 points, we're just gonna skip ahead here to visualize what I was just speaking about. So here we have blood lactate concentration in millimoles per liter, and here we have exercise intensity, okay? So again, assuming two individuals, and you think of, just a fixed volume. So they have the same amount of volume, or VO2 max. The untrained person, or maybe the same person if they're untrained, will hit this threshold. So you see this accumulation has a fairly steady rate as we increase the intensity, but boom, hit 50%. And all of a sudden, onset of blood lactate accumulation, which always occurs here at 4 millimoles per liter, is set. You get this exponential spike starting at about 50%. If someone is trained, they have, here it's illustrated till about 65, and then you can see it hit OBLA at about 80%. So all of this between here, like between these 2 points, this is all extra work, or extra effort or extra intensity that this individual can undertake exercise that this individual can't. Okay, so hopefully that kind of makes sense and helps illustrate things. Lactate threshold, very, very important to understand as far as intensities and workloads. We cover this more in lab as well. But understanding exactly what VO2 max is, and then what this threshold truly represents is, once you're crossing, a good example to help understand what this is if you know a red line in a car, right? You have a certain amount of RPMs. Once you go into the red zone in this revolutions per minute that the engine's working, you can really start doing damage to the engine, right? So while you don't do permanent damage to your body above here, you just kind of, you stop. The idea is above this line is your red line. So you only have a limited amount of time that you can handle above this line before you have to slow down to levels below your OBLA again, okay? Before the Cori cycle, if you recall what that is, starts using that lactate to make energy again, okay? So to touch on these last 2 points, again, lactate does not cause acidity, even though it's called lactic acid, and you might think acidity. That is not the case. The acidity comes down from the breakdown of ATP through glycolysis. You can go back to that lecture if you want to see exactly where those hydrogen protons are coming from. So if you get that buildup or backup of hydrogen protons that aren't getting soaked up by lactate, FAD, that's when we get performance decrement or decreases in performance. And I think I explained, as that lactate threshold increases, your performance increases. Okay, and I think just the last point there, again, one thing that you will see happen with VO2 max for individuals is that will increase as people train. So again, if you always have this threshold as a line and always this percentage, but you can increase the amount. So again, if you think a percentage of a pie, this untrained individual, their pie will be a lot smaller, and therefore the percentage will be a lot smaller, and their threshold is a lot lower. So the amount of work they can do before they hit OBLA, significantly less versus a trained individual, so whose pie is a lot bigger, so their 100%, that value is a lot greater. Plus, they can chew up a lot more of their pie before they actually start getting fatigued or hitting that red line by hitting their lactate threshold. Okay, I tried saying that a few different ways, just to hopefully have one of them land for you. That's it for this portion of the lecture. Cheers.